Welcome to this session on data science. Today, in fact, we will be dealing with linear regression. Before that, we will do a little bit of understanding on the machine learning and basics of machine learning, and possibly trying to understand very basic concepts. Of course, we will use them more and more when we are using them in the practical context. We would try to get an update of each of the topics. So under the linear regression, there are so many important topics that we need to get into, which we would be discussing. But yeah, let me see. There are a few queries from the people. Can you once repeat read_CSV to import a file? Okay. So there are two ways of or multiple ways of importing the data. One is from the files on your local system, right? Versus the other one is you can store the file in your Google Sheet and you can import. So here, if I am importing the file from my local system, I can simply say from Google Colab import files. And whatever is the name, you put file.upload. So once you say files.upload, you will get a kind of a choose files kind of a this thing. So you can very well click on this, and you can very well go to your location on your system, and you can select that file. Based on the file that you have selected, you can very well read the name of that particular file. Can we read the file directly from the website? So if the location or if the link of that, like if the URL of the website is there, you can very well read that location from the website as well. So if you are reading it directly from the website, I think there is a separate, linking URL. No, this is not the one. So you can just Google it. I'm sure you will be able to get it. There is a way. I have used it some time back. This is from your file system. This is what it is. So you give your URL, and I think okay, you don't need anything excess. So you can give the link of the URL, and you can directly say read.csv. So if you have a data lying in some kind of URL, so you can just give this, right? You mention the link and possibly you can give the, so you can use the same. So depending, I mean, sometimes you Google it out, I'm sure you would be able to get the solution. And after that, you just need to experiment with that solution. All right. So try that. And in case it's not working out, we can still see some alternatives, or you yourself can explore in the other domains as well. Okay. So yesterday we were just looking at the entire basic EDA that we would be doing. And possibly we would also want to look out for some kind of outliers. So right now, I would like to simply say, when we are identifying outliers in the real world, there could be univariate outliers, and there could be multivariate outliers, right? So we will deal with the outliers in more and more detail in the future chapters. But primarily what I want to say is univariate outliers, these are not erroneous values, first of all. Erroneous values are identified based on the minimum and the maximum. So if the minimum and maximum is allowed versus not allowed, then based on that, we are saying that those values could be erroneous values. So they are not, we are not treating them as outliers. Outliers are the ones, so the erroneous values, they have to be definitely deleted. Or you have to go for additional values or additional validation checks or additional, the new values corresponding to those, right? Whereas on the other side, we are talking about valid values only, but are very different from the rest. They are valid values, but are very different from the rest of the observation. So those are typically called as outliers, right? Because our objective in any data modeling, data science exercise is try to capture the patterns, right, which can increase the confidence of prediction. So if I am having all the values in a specific region with a very lesser standard deviation between the observations, possibly my capacity to capture the pattern will be much higher. The accuracy of the pattern will be much higher. Rather than that, on the other side, if I simply look at a few observations which are very different from the rest, obviously the entire pattern could be, the overall pattern now will be a biased pattern. So keeping that in mind, what is essential is better identify those extreme values which are differing more from the rest of them. So here the deletion means, or here the handling means, separate out those values from the rest. Possibly create a separate database for those extreme values. And see if there is any other model that can be built to handle them, which means the more and more separations you are doing, it means that you are trying to build a new model to address those variables separately rather than trying to combine them as a part of the original model itself, right? So there are multiple ways of identifying those outliers, right? Possibly one normal way that people look at is based on the set score. So for every observation you conduct, you create a Z score and you put some kind of a threshold to the absolute value of the Z score. So you may say that normally if that score is greater than 3, you may call them as kind of outliers. But generally, this would result in a very large set of numbers. So possibly you may want to keep this to a 4 or something to ensure that only very extreme values are getting identified as outliers. Similarly, I can think of one more mechanism called the interquartile range-based mechanism, where a very traditional approach is you put a limit like Q1 minus 1.5 times the interquartile range, or Q3 plus 1.5 times the interquartile range. So if a value is actually outside this limit, you may call them as suspicious outliers. But in case they are much more wider, right? Probably I say Q1 minus 3 times the interquartile range plus like Q3 plus 3 times the interquartile range. If the values are beyond these limits, then we may say that they could be a serious outliers. So I am not right now talking of what you want to do with the outliers. I'm only talking about these could be the possible outliers. Okay, what is Z score? Z score, okay, I made a mistake. I thought I discussed about it. Z score is nothing but from every observation, you subtract the mean of that column and you divide it by the standard deviation of that column. So by doing this, what generally happens is every column will end up with a mean equal to 0 and a standard deviation equal to 1. So this is what is like a standard normal. You are creating it at a standard normal value. So the standard normal value is otherwise called as your Z score itself. Okay, the Z score typically is nothing but you are subtracting the mean and dividing it by the standard deviation. So this way, normally in a normal distribution, we say if the data is following a normal distribution, 99.7% of the observations, they lie within plus or minus 3 standard deviations of the mean. So only 0.3% of the observations, they might deviate from plus or minus 3 standard deviation. So if you want to be a little bit more, if you want to allow for that also, possibly put 4 standard deviations where the proportion would be very minimal. So if at all you are having some observation which is radically deviating from even the 4 standard deviations, you can very well identify it as an outlier. So similarly, we can have, I hope you got it now, Dev and Prachiti. I thought that is something known, but yeah, I made my mistake. Yeah, fine. So this is one approach. The second one is an interquartile range kind of an approach. Or the third thing is a range-based Z score. Instead of mean and standard deviation based Z score, we talk about a range based Z score, which is nothing but every observation I subtract the median and I divide it by the mean absolute deviation. So instead of using the mean, I'll use the median. Instead of using the standard deviation, I'll use the mean absolute standard deviation. And this is actually multiplied by some constant 0.6745, which is approximately equivalent to your 2 by 3. So it is multiplied with that. And based on that, again, you can set, that is what is called as a ZR score. And based on that ZR score, you can very well say if the modulus of that ZR score is, let's say, more than 4 or something, I will call it as an outlier. So these are the different versions of outlier identification that you can do, right? All of them, the intention is identify not too many outliers, because I want something that is well deviating from the rest. Just a notional deviation, I'm not much interested, right? Something is very widely deviating from the rest, I would like to handle them, right? So sometimes what I may see is, if there is a large data that is coming as outlier, I will still increase the limit and then see which observations are still further away. So if, for example, I'll show you what I do generally. Yeah, let's say here, I'm doing a Z-score based outlier identification. As you see, I have defined one function where I'm talking about the mean and the standard deviation computation. And I am simply looking at computing the value, observation minus the mean divided by the standard deviation. And if that value is a kind of outlier for me, here I am setting the target as 3. So if at all I am seeing any specific value that is more than 3, I'll call them as outliers. Okay. So for each column, I'm doing this exercise. Now what I could see in loan amount, I have 25 outliers. In loan amount, I have 25 outliers. In term, I have 38 outliers. Property value 48. So if I go ahead removing all these outliers, it might become a kind of a bigger data loss. I'll talk about some of the ways in which we can reduce the outliers, possibly in I think after 2 or 3 modules, where I would be covering about the data preparation mechanisms for model building. Okay, what is I? So we are simply saying this one, right? Whatever are the variables that we are giving. So if you are really looking at, I am giving, so I'm actually calling this, I'm taking a column, one column at a time. So I am passing a column as an input into this Z-score outlier. So every element of that column, will be taken. For every element, the mean of that column, the standard deviation of that column will remain the same. So I subtract the element value minus the mean of that column divided by the standard deviation of that column. So the input that we are passing on is like a column of data. On that column of data, I would be computing the Z-score, and based on that, if at all it's an outlier, it would be treated as an outlier and it would be outputted out here. Is that fine, Dev? Or are you referring to something else? Okay, so then what we are saying is, if there are too many outliers, I am more interested in knowing which of them are very serious kind of outliers. So better keep increasing this. So let's say you talk about 4. So you see some of them have come down, right? So there is only one outlier here. Possibly I may want to handle it. If I say, let's say even 5 plus. So I want to see how extreme. Now these 18 are still extreme. This one is still in the extreme. Here in lower amount, there are, so basically after 5 or 6 also, If I'm still seeing that these are very extreme, then they are definitely very much differing from the rest of the crowd. And the numbers are also very less, 12, 18. So I may think of deleting these 12 values or deleting these 18 values and taking them as separate data set so that I can model them separately. So that could be one more approach that I can definitely look at. So that is the way we would handle the outliers in the data. And there are many multivariate outlier mechanisms also. So these things, especially when we are dealing with models, so we will talk about a clustering based outlier identification, probably a DB scan based outlier identification. Or we can also talk about other model based identifications, like I can use a random forest based outlier identification. I can use a neural network based outlier identification. So when we are discussing about those specific models, we will definitely cover the outlier identification aspects also in those models. So we have a few intervention points where we would be looking at the outlier identification, and we would be taking up that exercise as such. Okay. So with this, I come to the close of this module as well, where we did a kind of a basic exploratory data analysis. Okay. So this is so basically I think we have already shared this file with all of you. So possibly look at it, and I think I may have to share it again because some changes have been made. Or I think because the sharing is via the link, if you click on that link, you will get the updated file itself. So I don't think I have shared the files, right? I'm sharing the links only, the notebook links. So you would get the updated file whenever you are accessing. So with that, I come to this module 7 also being completed. So in case anyone is, so what you have to try doing continuously is, wherever you get an opportunity, you take some data sets and you try to practice on those data sets heavily. That is the only way to learn, right? There is no other shortcut way to learn anything. The more you get your hands on for the data, that is what makes you more comfortable. Okay. So now, before I get on to the understanding of the base model called linear regression, some of you may be very much conversant and comfortable, but possibly by understanding a linear regression in much more depth, there are so many concepts of machine learning and all that could be understood. Okay. So when I talk about machine learning, I'll just give you a brief introduction to what is happening here. What is happening? So obviously all of you are comfortable saying so the machine will try to learn from the data. Right? So the machine will try to learn from the data. Obviously, we'll have much more details as we move forward. So sometimes the learning could be a target-oriented learning. Sometimes that learning from the data could be a target-oriented learning or primarily a guided learning. And that is why it is called as supervised learning. So which means I have a target. I have a target to be achieved, or I have a target variable to be predicted. So the prediction as a task comes under this supervised learning. So I have a target. I want to use my variables to try to predict this target, to try to learn in such a way that I can understand the relationships between the target and my drivers. So I am having some driver variables towards the target, which are officially called as features. So features, variables, drivers, I am trying to build, let's say if these are all called X's and if the target is called Y, I am trying to build some kind of functions on the top of the X to be able to predict the Y more appropriately, right? So this kind of a learning where I have a target and I am trying to learn in such a way that my output, my learning output will closely match the target. So that kind of a learning is called supervised learning. And in the supervised learning, we have two major kinds of problems. One is called as a classification problem. The other one is called a regression problem. So the only difference is when my target, the target which is what I'm guided towards, if the target is a categorical variable, it is called as a classification problem. And if the target is a numerical variable, it is called as a regression. So whatever is the target, I am learning purely in line with the target to ensure that whatever is the output of my learning, it is in line with my target. It is coming closer to my target. So to ensure that I am going very close to my target, right, I would be using different mechanisms to go closer to the target. And that is where if the target is a categorical target, categorical variable, it is called as a classification problem. If the target is a numerical value, it is, so basically, okay, two targets. You look at the target here, till now in our example, we had status as a target. The status has only two values, default, no default, not default. So this is what is my target, because my intention is to predict whether the person will default or will not default. So it's a category that I am trying to predict. Whether a person will get a A grade or a B grade or a C grade. I want to try to predict the category. So my target is a category. So these kind of problems are called classification problems. Whereas there could be some problems to predict price, to predict quantity, to predict claim amount. So in these cases, the target, this is what is my target that I want to predict, marks. So I want to predict something. So these predictions are numerical values. right? These are not categories high, low, or something like that. I want to explicitly predict the value, the best possible value. So in that case, these problems come under the regression problem, right? So if we have to say, I want to do a prediction as per the world of machine learning, broadly, there are two major problems of prediction. One is the classification problem. The other one is a regression problem. Only two problems. To a large extent, of course, we can very well differentiate a little bit here and there, but majorly two kinds of problems: a classification problem and a regression problem. So when the target variable is a categorical variable, we call that as a classification problem. Probably what we have taken up till now, the default versus the not defaulted. So that could be a classification problem. If I take that same data set for our prediction, we can say that we are trying to solve a classification problem, right? So otherwise, if it is a numerical value that we are trying to predict, we call it as a regression problem. And what we will be seeing is there are many algorithms. Algorithms are like your functions again. There are many algorithms which can solve a classification problem or which can solve a regression problem. So we have different sets of algorithms for classification, different sets of algorithms for regression. There could be a few algorithms which can fall in both the categories, but of course, internally the mechanism that is used is different, even in those algorithms, right? So the next few sessions, or not few sessions, I mean, probably we'll still have to wait for a couple of more sessions. So our intention would be to use different algorithms, to understand different algorithms, and try to see to what extent we can do a proper classification or a proper regression. So this is one kind of machine learning. I hope whosoever has asked the queries, especially Nikita, it is resolved. I'm not sure about others. There's no specific query from others. So just wanted a confirmation from Nikita. Right. So then we could also have in machine learning, we have a second category called unguided learning. So no target. So nothing to predict here. In the supervised learning, there is something to predict always. Whereas in the unguided or otherwise called unsupervised learning, there is nothing that we are predicting. The major objective is pattern identification. How well I am able to identify the patterns in the data. So possibly a similarity. Novelty. So this is where outliers come into picture. Right? Something different from the rest. Dimension reduction. So there are some such kind of problems where we are trying to so similarity is a very classic problem called clustering, right? Novelty and outlier reduction, dimension reduction. So these are some of the common kind of pattern identification problems that we could still do by learning from the data, right? So we are going to talk about a lot of these kind of problems as we move along and how to solve these kind of problems as well. right? So this is the broader scope for machine learning. Of course, I did not get into too much of details of aspects, but primarily a very high level view of what is happening. Most of the time what happens is I take the data, right? Just like the data we have been considering till now. If it is supervised learning, so the data will be splitted into features and the target separately. Some kind of learning will happen between these two. And by doing that learning, we do some kind of generalization, just like we learn, right? Possibly let's call it as a book and let's call it as a question paper in the exam, right? Previous question paper. Let's call this as a book and let's call this as previous question papers. So you would try to read something, learn something from the book so that your chances of answering this question paper will get very much enhanced. Everyone has their own style of learning, right? Possibly I will learn the subject in a different way. Nikita will learn the subject in a different way, and all other friends, they are going to learn the subject in different ways. So what we simply say is, so those different learnings, I call them as algorithms. And there is no one single way that is the best always. It all depends on what is the kind of material that is available and what is the kind of questions that are typically there, right? So what kind of learning is a good learning? There is no straightforward way to say. So all of us have learned things in different ways, but the best way comes out when I have to write an exam, right? Now depends on how that exam has been conducted and how many marks that I would have scored. Each of us would have scored. So possibly if some of us have scored very high marks, so we may say this way of learning is much better for this kind of exam, for this kind of subject, for this kind of exam. This mode of learning is better because the accuracy of the results or the success of the results has come out to be much higher in this model. So that's how different algorithms will be compared, and the best performing algorithm would be taken up as a shortlisting. So though we will be knowing as many algorithms as possible, but finally it is that one or two algorithms which have really performed in the finals, they would be more chosen. Okay. Is AI different from ML? ML is just a few learning algorithms, right? In AI, we have, yeah, I think our friend has already given. So in AI, we have various activities which can be kind of performed based on the results that you get here. So in ML, we are purely talking about whatever the data is available, to what extent I can learn it, I can create patterns out of it. But sometimes implementing all those patterns, reacting to the environment, lot of these things, they do not come under the purview of ML. They go as a purview of AI. Right? Possibly you can very well say ML, deep learning, all these learning algorithms, they are a kind of a subset of AI. Okay, so I think the question is answered. So this is what I think when we move further, we will still keep seeing a lot of these aspects, right? Rather than, I mean, I just wanted to give a brief about what happens in machine learning. right? And how are we coming? I mean, see, there are some algorithms, let's say a linear regression, which all of us are familiar with. So linear regression is a kind of algorithm all of us are familiar with. Possibly, if I have to talk about this, we simply say y equal to a plus bx plus some kind of epsilon, right? So we are trying to establish this y, which is what could be a target variable, and this x, which is what is a single feature variable. I'm just talking about a simple linear regression, right? And so we are trying to express y in terms of x. And our objective is to find out what would be the best coefficients a and b. Try to identify what are the best set of values for a and b. And how are we saying I want to identify the best set of values? I want to minimize, right? I want to minimize the error part. Now, what do we say minimizing the error? So if I am saying I am forecasting some expected value, the expected value of this y is coming out as whatever is the x that is available. So I have some coefficients a and b, which are kind of fixed values. Obviously, I'm getting some estimate called y hat. Now, obviously, these two can be very much different. This is what we are referring to the error. But of course, if I typically take the error in this form, the average error across all the observations would become 0, because the positives and negatives will cancel off each other. So what is generally taken, we say we define the error as something like this. We square the error and we try to, I want to minimize this. This is what I think the standard procedure called ordinary least square. So I would try to minimize this error. And I would like to find out what should be the coefficients here. So that is what is a typical concept of linear regression, right? Now, here, now how do you find out these coefficients? Sometimes if you just go a little bit more deeper, right? So if I'm saying y hat is equal to some a plus bx, right? So your epsilon now, y minus y hat. So if you are saying this, so if you want to minimize your error, so you want to minimize this one. So you want to minimize the epsilon means you want to minimize this. So you can very well say I want to minimize y minus a plus bx whole square. So I want to minimize this. So this is what is my error. I want to minimize this error. So possibly you can very well find out if you want to minimize this error, you can very well do a kind of mathematical formulation, right? So if you want to minimize it, you take the first derivative. So possibly if I'm calling this as error, you take the first derivative of this with respect to a and minimize and equate it to 0. You take the first derivative of this with respect to B, you equate it to 0. So you could very well find the derivative of this with respect to A is nothing but A plus BX, and possibly this is so for A it is a kind of a constant. So here you can very well do this 2 times y minus A plus bx times b. So this is what you can typically call it as a kind of your derivative, and you are equating it to 0. So you can very well say here y minus of A plus bx equal to 0. So you are x here would be a kind of an expected value. So this is something that you are adding up across all. So you can very well say sigma y minus this is typically 0. Based on this, you can very well find out the value of A. Similarly, here also you can find out the value of B. So basically what is happening is the coefficients A and B are typically being computed. So we don't need to get into, I mean, possibly when you are writing your actuarial science exams or any other exam, you might have already got into the derivations aspects of all these things as well. So it's something that you might have already gone through this, but typically we are saying in the machine learning world, we will try to solve these kind of problems, right, using a mechanism called gradient descent. I will come to them, but we will be slowly covering some of these aspects. So that's where I want to start off with the linear regression to typically say how in the machine learning world, the system is trying to learn on an incremental way so that it is becoming a target oriented kind of a learning. So with that as a base, I think I'll get started with the linear regression. Of course, some part of it is theoretical, because you have to understand some important dimensions of linear regression, right, which is what is going to help you in improvising, because at the end of the day, we are talking of better predictability. Yeah, you can very well check. I have simply I have simply put up the derivation. My intention is not to derive. So the second derivative, possibly positive value of the second, you will end up with that, right? You will end up with that. So take the second derivative, a possible positive value for that second derivative. And based on that, you can very well conclude that this is the minimum value. Okay. So you can do the derivation. Probably I'm someone slightly not that comfortable with many of the derivations on the fly, right? So I mean, practically we don't do into the derivation. Once we know that this is what is the background, we simply move forward to execute them with the data and all. So I mean, I've given you the direction on how you do it, but probably I might have made a mistake with respect to the computational aspects, because you see there are some sigmas that are missing, right? So possibly because of those sigmas, again, when you are taking a derivative, if something is missing out, just look at it and correct it accordingly. Okay. So otherwise, if I have to do a derivation, I think I should first write it out on a piece of paper. I should solve it before I come to the class, because on the fly doing a derivation is something that is slightly difficult for me, right? So because I would always play around with the codes and the data. So possibly solving a mathematical problem the mathematical way is something That will take some time for me to recollect and do the things. So if you are looking for derivations and all, then possibly I'll have to write them out on a piece of paper before the start of the class. Okay. So then I'm coming back to this linear regression concept. Okay. So till now, you are very comfortable with Python. We have just got a brief introduction to what is machine learning. And we did the descriptive statistics, basic concepts. So this is what we have typically done. Then here we bring in some technical jargon apart from the statistics jargon of linear regression. We bring in some technical jargon relating to the cost function, the gradient descent. So we will go slightly towards understanding the machine learning world. And I would introduce you to the linear regression algorithm. So here in Python, if I know this library called scikit-learn, if I'm aware of this library called scikit-learn, if I'm a master of this scikit-learn library, then I can do any amount of machine learning quite comfortably. And the scikit-learn has been created in a so beautiful way that every algorithm, the pattern of defining the algorithm is similar. So if you know one algorithm, how it is defined, how it is executed, I'm sure all other algorithms can be executed, even if you don't know what is the mathematics behind that algorithm, even if you don't know what is, how that algorithm typically solves the problem, even if you don't know any of those technical or mathematical aspects, from a solution perspective, you will be able to solve that problem because scikit-learn has created a very user-friendly kind of an interface for the same. So we will be discussing about that aspect as well. And how do we evaluate? So these are some of the things. And of course, I would also talk about the assumption. These are purely the textbook related stuff, right? It is very important to understand the assumptions because many a times I keep seeing people that they ignore these assumptions that are driving. And sometimes that may very well lead to statements like linear model, linear regression does not work at all. We need to go for sophisticated models, etc. Or people keep talking about a random forest or some such kind of fancy names, and they always say those models are much better than the linear regression. So from that perspective, I want to add some value to bring out all these concepts. So sometimes it might be a little bit boring for people who are well versed with linear regression concepts, but definitely for the benefit of others, I would like to spend some time. So we are talking about, we are introducing the words called predictor and target. I've already introduced them. Target is always something that we are going to predict, and predictors are something which are helping us in predicting the target. So we use the values of predictors to predict the target. Now, in this context, I want to bring in one more important information for you. So generally, let's say we have some predictor variables and there is one target variable, right? So most of the problems have to be created in such a way that the predictor variables are known at the time t. So whatever is the time that we are talking of, I should be in such a way that the predictor variables are known already at time t, and the target variable is unknown at time t. Right? Your problem should always be like the predictor variable is known at time t, the target variable is unknown at time t. Probably it might be known at t plus delta. Probably it becomes known at t plus delta, but at t definitely it is unknown. That means I am trying to use my history. So basically what is happening here, let's say we have talked about our same problem, default versus no default, right? So I'm taking at the time of loan application, So that is what we are talking of as time t. So possibly the age of the person, the marital status of the person, the loan type, the rate of interest, right? So like that, there are so many variables that are considered. What is the loan amount? What is the property value? So all these observations are known at time t. But what is unknown is whether the person will default or not. I don't know at time t whether this person will default in the future. So the default can occur, let's say somewhere from time t plus delta to, let's say, t plus 5 years. So the default can happen anywhere during this period, but this is a future. So I want to understand to what extent I would be able to know this, I would be able to predict this at time t itself. So sometimes people create problems saying possibly they take all these values. So I got one assignment some time back. I mean, people created one assignment, some of my students earlier. They took some variables, right? Something which was very unusual. That's the reason I remember. They took the height of the people, they took the weight, and they took some other characteristics and said that these are the predictor variables. And they took the outcome variable as the target variable is gender. So predict the gender of the person based on some of these characteristics. It's a very ridiculous problem because we are talking about, we know the gender. Gender is the gender of a person. So if I had measured the height, weight of that person, I know the gender of that person also. I don't need this to be predicted. Predictor is always, I mean, the target is always something where you find some level of unknown characteristic of it, right? Just by, so when you don't know that value at time t, but you want to know it so that you can take a better action on it, right? So those kind of problems will come towards the prediction problem. So always ensure that the data that you are collecting, don't try to build on any such kind of a data. Always ensure that the data that you are using or the problem that you are solving, the X variables are always available ahead of time compared to the Y variable. This is something that I want you to appreciate because framing a problem is one of the most essential aspects. So most of the time, people are behind building models, but here model building is a very small part. The whole process involved in really developing this to the core will become the most important dimension. And I want all of you to focus on that dimension more rather than just going ahead in building the model. Okay, now income. You want to predict the income. Okay. Yeah, income is one of the variables. So depending on which variables are known and which variables you think can drive the target, we will be collecting those variables. Okay, so we'll be talking about that. Then we will do some simple plots, which we have already done. The prime intention is to see whether there is any relationship between the predictors and the target. So here, linear regression is a regression problem. As I've already discussed, there are classification problems and regression problems. Regression problems are the ones where the target variable is a numerical variable. So in a typical regression problem, I am predicting a numerical variable like price, income, right? Probably income 1 year down the lane, or the price of a particular product, or I can talk about the sales of a particular product in the next 1 year, or the claim amount on a particular policy. So these are some of the problems that I can solve using regression. Okay, so we will try to look at kind of scatter plot because we have already discussed about the scatter plot. It is plotted between two numerical variables. It will tell you whether there is a kind of upward relationship, which is a positive relationship, or a negative relationship, or almost a flat kind of a relationship between the variables, right? Then we are talking about linear regression, dependent, and in some points you are much aware of. But here my intention is to introduce you to this cost function and the concept of gradient. These are two important values that we are going to talk about because this is the concept that we are going to use everywhere. Okay. Then how do you do the linear regression algorithm in scikit-learn? And possibly we move from a simple linear regression to a multivariate linear regression. And finally, how do you assess the goodness of fit of the model? And what are the various assumptions and so on. So we would typically do some basic scenarios here. We would import some necessary function, right? Pandas, numpy. So this is something that we are doing. But along with that, I would also import the linear regression model from this scikit-learn. Scikit-learn is a very powerful library for machine learning. So it contains a few dozens of machine learning algorithms. All are handled more or less in the same manner. All right. So I would be importing this function as well. Linear regression is a function that will help me to perform linear regression. So I can do it in 1 line or 2 lines of code, but better we will understand it in much more detail. So initially, I'm going to work with univariate analysis, which is otherwise called as simple linear regression. Okay. So we are talking about a simple linear regression. I'm taking a very another data set because till now, whatever the data set that we have worked on, it is going to be mostly a classification problem. So when we take up the we will be working between, we'll be switching on and off between the classification problems and the regression problem. So because this is a regression problem, I'll have to take another data set. I'm considering a very simple data set. Possibly you can very well work in the background on complex data sets, right? Because when I am demonstrating something in the class, a simple data sets are much more appropriate to be taken up. So I am trying to download the data from my Google Drive. So I am changing the directory to this folder. All my files are, all the files that are required, I would be keeping them in this location, and I would be accessing this particular location. So IAI data science is what is the folder, and I have changed the directory. So now from there, I have picked up the simple example called medical expenses.csv file. And this particular file, it actually contains, so show the link, okay. Yeah, how to pick up. So you can click on this. So once you mount your drive, you can click on this. You can click on this drive, my drive, whatever is the folder structure that you have kept. So I have kept something called Colab notebooks, and I could see that I have a folder called IAI data science. And in this, all my modules are there, right? Possibly the medical expenses file is here. I'm saying copy path. So if I'm directly linking the file, I can do this here. Whereas if I'm talking about directory, I stop here. So I copy the path for the directory and I paste. So basically when I'm referring to files in this particular directory, I don't need to put this entire path because I have already frozen this path. Is that what are you referring to, Vimal Kumar? So once you do the mounting of the drive, it is much easier. You save all your files in the Google Drive and it would take care. I mean, you just need to point to that location and pick it up. You don't need to maintain any data on your local file system. And once I have changed this directory, I would be working only in this directory. So within this directory, I'm looking for this particular file called medical expenses, and I'm reading that particular file. Is it fine, Vimal Kumar? Okay. So then this particular, probably without doing this, if I look at only this, you will see that, okay, I did not import pandas. I have, right? I did not run this line. Okay, looks like I did not run that line. So OS is your operating. So this OS is a package which contains this OS is a library that actually contains this change directory kind of command. Right? So that's where we are writing OS. OS is another kind of a library, just like your pandas and NumPy. OS is a library. So within that OS library, you have this mechanism of change directory, right? Then, so if I'm simply looking at the whole file, I have these. So basically the problem is, so first let me define the problem. So the problem is predict annual medical expenses for a person, for an employee. So this could be, who would be using, let's say a health insurance company may want to understand what is the typical annual expenses of this of each of employees, so that they would try to offer some kind of they can design some kind of insurance products, and they can offer that product by taking some premium. So they would be more interested in trying to identify what are the annual medical expenses for each of the employees. Now, obviously, they should get some historical data, right? So what is that first they require? Okay, take some sample of people. You take some sample of people, right? For each of those people, possibly at the beginning of the year, you take some of their characteristics. So in this example, possibly they have taken the age of the employee, right? The sex of the employee, the BMI. These are all available at the beginning of the year. How many children that particular employee has. This is also known. Whether that employee is a smoker or not, and possibly various what kind of region he belongs. So there could be many more, depending on the subject matter expert discussion. They might give me many more variables regarding this particular employee, which might influence the medical expenses. So at the same time, over the next 1 year, what are the medical expenses? So which means I would, let's say, collect the data as on Jan 1st. My X values, let's say, are collected as on Jan 1st, 2022. That is when I collect all the X. From Jan 1st, 2022 to December 31st, 2022. During this future period, as of Jan 1st, this is future. But as of now, it might be past. But as of Jan 1st, it is future. So during this period, what were the expenses? So basically, if you look at, this is happening at time t. These are the ones that are happening at time t plus delta, right? So within the next 1 year. So that's where probably I want to see, with the help of these values which are available at time t, how well I can relate them to this value, which is available at t plus delta. So what could happen is, the moment I see that this is what are the characteristics of a new employee, I will be able to predict what could be his expenses. I don't know how accurately, I'm not using the word accurately. I will be able to predict what could be his expected expenses, so that accordingly I will suggest a specific policy to him or her. So that is what is the intention behind this exercise. So that is what is the story to this exercise. So we could clearly see that this is the data. But right now I want to just go with two variables, right? So we are talking about a simple linear regression kind of a model. So out of all these columns, I will be taking only BMI and the chart. So I want to see if BMI alone, to what extent I can predict using the BMI alone. So that's the reason I am taking only two columns out of that 7. One is a BMI column, the other one is a charges column. So obviously, you know, the predictor is the BMI and the charges are the target. Now, you can very well say, why only this way? Why can't charges be the input and BMI be the output? Now, if you don't know who the person is, right? Possibly if you don't know who the person is, you are not even able to measure. You create a different story out of it and you want to predict. So logically speaking, BMI is something that is directly measurable and it's not a futuristic thing, right? We are, or if you say the BMI 5 years later or something like that, right? Next year BMI based on the this year's charges. But sometimes the problem does not set well, right? BMI is something that is directly measurable, right? But if you say I'm talking about the futuristic BMI, then probably it is still a future variable. And then you will have to identify what could be the drivers for that futuristic BMI, right? So charges, whether they are the drivers for the futuristic BMI or not, you have to sit and discuss and decide with your team. So in the regular problem, the BMI is the predictor variable and the charges are our target variable. So we are simply doing a plot, you could see here, right? I'm doing a scatter plot. I'm taking the BMI on the x-axis and medical expenses on the y-axis. So I'm simply getting a plot and overall it looks like there is an upward trending, right? Possibly I could see that as the BMI is increasing, overall I see that some medical expenses are at least increasing. In some cases, I am still seeing a flat, but at least in some of them, I see some kind of an upward trend. As the BMI of the person is increasing, I am seeing that the medical expenses are also increasing. Now, so that is the basic association that I could see. Now, what we say is, right, I want to have a simple line, the best fitting line. I want to have the best fitting line which could capture this relationship. And I think all of you know that that best fitting line is what is traditionally called as the regression line, right? That best fitting line is what is typically called as the regression line. Now let's say I'm plotting some data. Just like that, I'm drawing one line. So I'm drawing one line where I'm taking X value as 40. Or possibly let me take the X value as 30. I don't know whether I have plotted all these. So let's say I'm plotting one line where X value I'm taking as 30 and I'm plotting a line. So is this the best line? I don't know, right? Similarly, I'm plotting some other lines. I'm taking 5,000 plus 100 times BMI, 1,000 times BMI. So I'm just creating some lines. So A plus BX form, 5,000 plus 1,000 times the BMI. So this is the kind of a line that I got. Is this the best line? Or 10,000 plus 600 times the BMI? Is this the line? Or 3,000 plus 1,200 times the BMI? Is this the line? So what is that we are saying? Or if I plot all of them together, this is how the lines have come. Which one is the best line? Right? So we have to really work out and see which of these lines is the best line, or is there any other line? So you could clearly see that the medical expenses, they are, the predictions for the medical expenses, they are changing drastically. Possibly in some cases, the change is to the extent of 10,000 also. So in some cases, the expenses are very high in some models compared to the other models. So they are very much changing. So which one is the best line? Or is it any other line that is going like this? Which could be the best line? So which means we need to have, now this is what is the base. We need to have some kind of a function. We need to have some kind of a function which will say how close are we going to the actual value. When I'm using A plus BX to predict, when I'm using A plus BX to predict, I need to have some kind of a function which will tell me how close I am going to the actual value, or how far I am staying away from the actual value. So that is what is something that I require. So I can very well take what is the actual value and what is it predicted based on my line. Based on the line that I have taken, what is predicted? So how close is my predicted to the actuals? So that is what. So we have to know, we know what is the actual, we know what is the predicted. We want to see how far, we want to have some kind of a function or some kind of a metric that typically tells you how far or how close are we from the actual. Obviously, if the points are very far off, actual and the predicted, if they are very, very far off, right, it should cost me more. It should cost me more because it's a wrong function altogether. It's a wrong model altogether. It's a wrong line because I'm deviating a lot from the actual. So the penalty should be much higher. The more the predicted value is deviating from the actual value, the penalization should be much higher. So that kind of a penalty function, that kind of a penalty that we put for the difference between the actual and the predicted, which means what is that we are saying? I am predicting the Y, predicting the target. Just understand this. I am predicting the target using a linear function of the predictors. predictor single. I am predicting the target using a linear function of a predictor. So I am actually predicting using this. So I am taking different values of A, different values of B, and I have got, let's say, Y1, Y2, Y3 as the predictors. Now, sorry, Y1, Y2, Y3 as the three different models. Now, Y is my actual. So I want something that would penalize. I want something that would penalize for the greater distance between the actual and the target. Now that is what we are simply calling as a cost function. The penalties, how do I capture the total penalties? And that is what we are calling as a cost function. And this cost function that we are using is nothing but the least squares cost function. So this cost function concept will become much important in machine learning. That's where I am coming referring to that concept. So here we are using a cost function called least squares cost function. Because if the gap between these two is very large, the error importance will be much larger. So because that's the reason. Otherwise, we could have used y minus y1 absolute. But absolute does not penalize bigger differences more compared to the smaller difference. All of them are penalized equally. Whereas the squared function penalizes larger differences more compared to the smaller difference. So that is where the cost function that we would be referring to in most of the regression problems, the cost function that we would be referring to is this least squares cost function. And we want to minimize this function to get the best fitting line. So we have already derived that, because if I have to minimize it, we have already discussed about it. You take the first derivative, equate it to 0 with respect to each of the weights. And that is how you come out with the cost function. I mean, minimizing the cost function to arrive at the parameters of the model. So linear regression as a model, now you have to understand every model that we are talking of, that model has a function. So now every algorithm that we bring in, there will be a function that links predictors to targets. So there will be a function that will link predictor to targets. That's the first thing. There will be a cost function that would compare actual with predicted. Right? And there would be a, so the second step is there is a cost function which would compare the actual with the predicted. And then there should be a mechanism that would improve on the prediction. There will be a framework or a mechanism that will improve on the prediction. So the linear regression, it uses least squares cost function. So the function to predict the target, we have already seen. This is a linear function. Then the cost function is the one that is trying to compare the actual with the predicted, which is called as the least squares cost function. So that's the reason you would also have used the words like OLS regression which is ordinary least squares regression. That is what we used to call even for a linear regression. So you are able to analyze the relationship between the two quantitative variables, and we can derive some meaningful insights from that. Now, explicitly, we are talking about medical expenses as the target variable, or in the linear regression world, we'll call it as the dependent variable. And the predictor variable, which is the BMI, in the regression world or in the statistics world of prediction, we call it as an independent variable. Since we have only one predictor, we call it as univariate linear regression or a simple linear regression. But in most of the problems, we'll have multiple predictor variables. So we'll call it as a multivariate kind of a regression. Multiple regression, multivariate kind of a regression. Can we consider the link function is same as the GLM? Yes. So in GLM, possibly you can model many number of variables, right? You can model GLM. Possibly you can do a logistic regression using a GLM. You can orbit regression using GLM. You can even model the linear regression also using a GLM. So, GLM is like a more generalized version of the linear model. Okay. So now, why are we bringing this cost function? Obviously, predictor, feature, driver, independent, explanatory, these are all the same names, right? Variable is also, sometimes feature variable. So all the names, explanatory variable, all these are the same name. Okay, again, because the knowledge is coming from multiple domains, the terminology also started mixing from multiple domains. So why are we talking? Obviously, we know that the predictions and the actuals will always deviate. Only in ideal situations we can think of the predictor variable predictions will be 100% accurate. So I need some kind of a measure which is more robust. And as we have already said, the gap between the actual and the predicted value sometimes need to be captured in such a way that if the gap is higher, the penalty should be higher. And if here, the generalized way of talking about any model. So this is the way possibly you can think of this as an error function or a cost function. Sometimes we even use the word called error function for a cost function. You see, there is some function with some parameters theta, which is taking the x values. So in our case, in linear regression, it is a plus b, which is linear function of the x value. Where function of the right now in a linear regression, it's a simple linear function of the x values, right? And I am taking a y value corresponding to that, subtracting squaring. So that is what, and I am adding across all of them. Actually, it is 1 by m, but to facilitate some kind of differentiation and all, sometimes we compute the error function as 1 by 2m. Otherwise, we simply take the average. Average works out as 1 by m. But because you would be seeing later when I take a derivative, the 2 and 2 gets cancelled off. And that's the reason we have been talking about 1 by 2m. Just for it, because multiplying or dividing by a constant does not alter my result. Okay, so what we are saying, every model that we are going to work out with, that model will have some parameters. Every model that I am going to work out with, every algorithm that I am going to work out with, that particular algorithm will have some parameters. Using those parameters and taking the x values, which are the predictor. So just understand this concept, right? I mean, you might all be comfortable with regression, but this concept I would be linking to the other algorithm. That is where I am trying to spend some time here. So there is some function that I am creating. In this case, it's a linear function. I'm subtracting the actual value. So this is like a predicted value. Subtract the actual value, square it. And this is for one instance. So like that, we have m different instances. You sum up across all and you take the average, which means you divide by m. But for some specific advantage, we divide by 2m. So this is what is a mechanism or a cost function that captures the difference between the predicted values and the actual value. So this is called as the cost. So this is the general cost function that we use for all the regression model. This is the general cost function that we use for all the regression model. So theta is typically the parameters. So in case of linear regression, where we talk about y equal to a plus bx, a and b are the typical thetas that we are talking of here. So they are the parameters of our linear model. So we are simply talking of, let's say if I'm talking about b, a plus bx, if x is changed by 1 unit, by how much extent is y going to be impacted? That is what is the b talking about, right? And if the value of x is 0, how much would be the value of y? That is what is being mentioned by your a, which is the intercept term. So we have to find out what is the optimal value of the intercept or coefficient so that the overall cost function is minimal. Now, if I am doing it the pen and paper way, obviously I can simply say I will derive it, right? 2 times I will take a derivative and I would take a derivative, I'll equate it to 0. I'll find the values of a and b. So that is like a closed form solution. Oh, is my voice still breaking, Dave? I think I developed a sore throat today, right now. So I don't know whether it is clear or breaking because my voice itself is getting stuck now. Okay. So H is a simple function. Think of it like this. H is a function of X. So that particular function is having some parameters called theta. So in a linear regression, H of a comma b is a plus bx. So H is a function. So there's a linear function of a and b. It has two parameters called a and b. And this is entirely a function of x because x is the variable that we are considering here. So we will take, there are m rows in a data. So we are taking the predicted value minus the actual value whole squared, summing it and dividing by 2m. Now, yeah, I'm coming. So basically what is that we are saying? We know that the total cost function right now, the total cost function is 1 by 2m times sigma. So we are saying a plus bx1 or x minus y. So a plus bx is nothing but my h theta of x. All right. A plus bxi minus yi whole square. So I want to minimize this. Now, what is that we are saying? I'm not looking for a closed form solution. I am trying to look out for some alternative. You'll see this. If I say that this is my error function or cost function, I am trying to minimize this cost function with respect to the parameter A, and I am also trying to minimize this cost function with respect to the parameter B. So if I have to do that, it is 1 by 2m 2 times sigma a plus bxi minus yi, and with respect to a, the derivative is constant. Whereas this one, 1 by 2m times 2 sigma a plus bxi minus yi times this is xi. I am trying to do a derivation of this. So what do we say here in the world of data science? What we say is, rather than equating it to 0, right? So if it is a statistical way to derive a closed form solution, what I'll do, I'll simply equate it to 0, right? I'll say simply a plus bxi minus yi, or possibly I'll do sigma axi plus sigma bxi squared minus sigma xi yi is equal to 0, right? And based on this, also here I can say the same, sigma a plus bxi minus yi equal to 0. So sigma a, when you are summing up across 1 to m, so sigma I equal to 1 to m, so basically it will be ma plus b times sigma xi minus sigma yi equal to 0. So you can very well try to arrive at finding out the value of b. And here also you can very well, now you have a kind of a linear equation in a and b. You can very well solve them, you can get, right? 2 in the denominator is just for an adjustment. Don't worry about it, right? 2 is just to ensure that when I take a derivative, they get cancelled out. Nothing more than that. Even without a 2, you can still manage the show. Okay. So now, what the machine learning way of working out is, I don't derive this like this. So I have this one, right? I have simply taken. So basically, this is becoming the summation of whatever I have predicted minus what is the actual. And I multiply it with the x value. So this is what is the derivative that we have got. So rather than equating it to 0 or something, what we simply say is, we take some kind of a very small value called a learning rate. So this is actually the gradient. This is what is the slope. This is what is the slope. B is what is called as a slope, right? And this is what I have computed as the slope. Slope has another word called gradient. So what we keep saying is, let's say right now, let's say this quadratic error function will look more like this. So what we will say is, right now, let's say we are at this kind of an error, right? So I will find out what is the slope of this particular curve at this point. This is what is the gradient. So what I'll say is I will go down by a little extent. I'll put something called a learning rate, and based on that learning rate, I will take the values, I will change the values. So initially the B must be having some value. Now I will adjust that B by, I will change the B in such a way that I will take the slope. The slope is coming out as y cap minus yi times xi. I'll take the slope. I'll multiply this with a learning rate. I'll take a small value, let's say 0.001. Right? This is what is my error. This is what is my value of x. This is what I call as a learning rate. So based on that, I will compute a new value of b. Call it b dash. And similarly, I can compute the new value of a. So the existing value of a, the slope is simply y hat minus yi, because it does not have a multiplication. So the slope here is y hat minus yi. I will not multiply it with xi, and probably I'll multiply it with a learning rate. So basically, I'll get a new value of a and b. I'll use these new values of a and b again to fit one more function, right? Then again, I can use a cost function. Then again, I will use gradient descent. So this process keeps iterating till I am able to achieve the best possible error. So which means on this error curve, I keep coming down, 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 and possibly I get the least possible error. So sometimes if my learning rate is very high, possibly I reach much faster, and it might be possible that I would omit this minimum and I'll go much below again back. And at the same time, if this learning rate is very slow, I'll take a lot of time to reach this. So sometimes the learning rate, optimal learning rate would actually reduce the number of iterations, but at the same time, it can go more and more closer towards a better prediction as well. So this kind of a mechanism where I take the slope of the error function and multiply it with the observation, and then come down towards the new prediction of the parameters in an iterated fashion is what is the mechanism of gradient descent. So we are computing the parameters in a machine learning algorithms in iterative fashion by using this mechanism called gradient descent. So we are trying to choose our thetas. Thetas are nothing but the parameters. In this case, the thetas are a and b. So I want to choose theta for minimizing. Now you can say, why am I doing all this? Why not I use a simple mechanism, which is what is why not I use a simple mechanism, which is what is a differentiation equated to 0 and get a closed form solution. Now for this linear regression, we might still get that closed form solution, but for many other algorithms, getting through a closed form solution might be very much difficult. So what we say is, in a gradient descent, you start with some initial random values of a and b. You start with initial random values of a and b, and you keep making changes. As I have already written, your new a dash and your new b dash will be computed through this mechanism. So you keep making changes to the computations of a dash and b dash until we keep getting the minimized value of the cost function or the error function. So we are repeating this mechanism in an iterative fashion by using a small value called alpha, which is the learning rate. So the new values of B dash and A dash are updated based on B and A by doing this kind of a simple operation. So this is what is a intuition, because when you get into other algorithm, you will get much more comfort when you understand that gradient descent is a way to come out with the new value of parameters from the existing value of parameters, right? So we would always see that this mechanism would be a kind of a helpful thing for you. Now, batch gradient descent, as we have already seen, right? I have taken the entire, now here this is like an individual. For each individual, we are finding out the step-by-step process of B dash and A dash. Sometimes you can very well take all the observations together, or a set of observations, a batch of observations together, and you can update one single B value and one single A value for the entire batch. So that is what we call as a batch gradient descent algorithm. So initially you set some values for A and B. You will find out what is the predicted value for all those data points. Then you are simply looking at the total error, and you want to minimize the kind of a total error. So which means rather than doing for one observation at a time, when you do it for one observation at a time, we call it as stochastic gradient descent. When you do this exercise of new A dash and B dash for every observation separately, then we call that as a stochastic gradient descent. Whereas if we are doing for all of them together, then we can very well refer it to a batch gradient descent. And most of the times you will find batch gradient descent is much more effective in terms of time, right? So that is what is an intention. So probably handling it in scikit-learn, and then further improvising the understanding aspects of that. Because if you understand this lot of algorithms, you just need to know what is the function, what is the cost function, and how do you approach that. So basically that would simplify the learning more in the future. Batch size, I mean, it's not that straightforward. Possibly we will, I mean, you will have to iterate, because the batch sizes typically, it's not a straightforward way. Sometimes people try 2 or 3 different alternatives to see if the results are not that significantly changing for batch. All right. So implementing this algorithm in scikit-learn and probably moving a little bit more further, we'll take it up in our next session. So I'll stop this session here for today. Thanks a lot, everyone, for listening to this session. We'll again come back